Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
The afternoon session. The first one will be led by Nicole Imolika. Nicole is a researcher in algorithmic game theory in our lab.
Thank you, Christian. So, as you know, this lab was built with the idea of bridging the gaps between computer science and related disciplines, like economics. And so I thought for this session it would be a good idea to take a sort of step back and ask the meta question of what does it mean to do research at the intersection of computer science and economics, and how does it impact the research agendas and the way research is performed in each of these fields. So I thought to myself, okay, I need two prominent thought leaders, one from economics and one from computer science. They should be, you know, eloquent and outspoken and entertaining personalities that can enlighten us on this on this question. And immediately, Sergio and Christos came to mind, and if you know them, I think you know why. I have a lot of respect for them. Our first speaker will be Sergio. He's from economics. He's from the Hebrew University and has a lot of very important work in game theory. And so I would like to introduce Sergio, who will tell us his perspective on this intersection between computer science and economics.
Thank you. Yeah, I'm afraid you are going to be disappointed. I mean, I'm not sure that this is the kind. At least I gave yesterday a real talk, so now I feel that I can, you know, I did my duty, and now, you know, it's economics and computer science. So first of all, I'm not an economist, okay? So, but anyway, when you talk about economics and computer science, it's really a subset of economics. I mean, if this works, okay. So that's really economic theory, yes? And we are not talking about econometrics. We are not talking about labor economics or gender economics or whatever, different kind of labor, yes. So it's a subset. In fact, I'm going to talk about a superset of that, and that's game theory, okay? Which, so I'm going to talk about game theory in computer science. That's really, do you have something that works without real pressure? I don't know. It's, oh, okay, now. Okay, once I said it, it started working, you see. Okay, so I thought that I would start, I started listing in my mind some connections between the two fields, I mean game theory and computer science, and I started making a list, and it's quite a list, yes? So let's start with the obvious, which is computing solutions and the computational complexity in computer science. That's an old connection. I think Ehud had a paper, right, in the very, very old days, you know, when these connections were. So that's clear connection, okay? So now, next thing, okay, would be repeated games and what's called bounded rationality. So repeated games means repeated interaction that goes over time in more than one period. And then questions that are raised is, well, strategies in such models are extremely complicated creatures. And extremely complicated creatures are, well, you may prove theorems with them, but they are not very useful sometimes. So we want to limit ourselves to simple strategies. That's bounded rationality. And that's where computer science came in force, and computable strategies, automata, bounded recall, bounded memory, and lots of work like this. Christos had some early work, in fact. Again, it's before those connections really existed. Okay, so there is here a whole big field, yes, really big field. Okay. Okay. Then there is something that in game theory is called cheap talk. Cheap talk just means communication where you can say anything and it doesn't cost you anything. That's different than what's called signaling, which you can send a signal, but it may cost you, it may affect things. So that's called cheap talk. And there is this very strong connection to cryptography in computer science, but this is a place where there is really a missing link, okay? There are results in game theory. There are results in cryptography, okay? And I must tell you, I once, with a colleague, we sat down for 1 week, a whole week, well, 5 days, okay, whole work week, with some expert in the area, computer science expert in the area, in Jerusalem. We sat for 1 week, and we tried to understand what exactly computer science people know that is useful for game theory. Okay? Well, the end result of that 1 week, we could not get even one theorem. Okay? We'll always get something like, okay, if this is true, then we can reduce it to this, then we can reduce it to this, then you can do this, and then you get that. Okay, now let's trace it back and try to get a theorem where you can make assumptions about the game, about the strategy, something. We could not get it, I'm sorry to say. And there is still a gap here. I think there are important results in computer science in cryptography that have not been translated into game theory. And there is work to be done. Okay? So, invitation for somebody to get into that. I think it's an important area. Okay. Well, and again, the order here is not, it's just the order that things came to my mind. It's not any significance or importance or chronological, just some order. There is the area in game theory known as common knowledge, interactive epistemology. Computer science is reasoning about knowledge in distributive systems. So I don't have to tell you what those things are here, of course. And again, there are extremely strong connections here and work in both areas going back and forth. Okay. 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 Then there is another whole. Yeah, you have another one. Okay. Okay, I can do it. Then there is the area of in game theory of dynamics. Learning, adaptive heuristics, forecasting. I mean, those are all, it's a huge area with lots and lots of things. And there are many parallels. Let's see. Okay, so there are many parallels in the computer science community. So on one hand, there is machine learning, what comes under the label of machine learning and AI. All the what's called competitive analysis, offline versus online, where you start comparing things that you can do when you know everything in advance or when you know it period by period and so on. Then the notions of computational complexity become very important in order to get bounds on how fast dynamics or how slow dynamics converge or don't converge to whatever you want. Okay? Again, there are many connections here. It's a huge area. Okay? Then we have the Price of Anarchy that many of you, if not of you, know, which talks about equilibria and efficiency or inefficiency of equilibria and what you have to pay for that. There is mechanism design, okay? What in some crowd like this one is called economic commerce, or just EC, which by now I think no longer stands for economic commerce, but for economics and computer or something. Yes. So anyway, EC. Yes, whatever. Which again, it's a huge area. Now I must say, I remember in the 90s when suddenly at the Center for Rationality, I'm at a center in Jerusalem which has people from lots of areas, including computer science, economics, psychology, and lots of other things. So suddenly there was a seminar. I mean, Noam Nissan and Moti Perry started having a seminar, something on mechanism design and computer science. I had no clue what they were talking about. Why was it? Why were there any connections there and so on? So that was, but that has developed into quite a fruitful connection. And well, again, okay. Then there is a topic of coalition formation in game theory and the parallel of social networks. Again, it's a very, very active topic, I think, in computer science. It's also very active still in game theory. I think I have more things. Let's see. Voting and social choice, yes, which, well, I asked Noam, how is it called in computer science? Well, I said computational social choice, okay? So you can, okay, I think that's, yeah. So again, this is just a list. As you see, there are really many connections and very different connections. Yes, it's not just take a problem in game theory and say, okay, how long does it take to compute? No, no, there are much more deeper connections here, and each one of those is worth, 1 hour lecture at least, or 2 hours or something. So don't worry. Okay, where's my clock? Oh, I see. That's how long I have left. Okay, okay. Okay, good. So now I want to tell you some some stories. Okay, I have. Let's see how much time I have. There is a difference between the two disciplines. Okay, there is definitely a difference between the two disciplines, and I want to talk a little about that. But I want to start with one story or two. Let's see what the time permits. So first story is who needs another proof? Okay, and the story is about correlated equilibria and dynamics. Okay, so what's a correlated equilibrium? Okay, well, doesn't matter if you know or doesn't know at this point. I mean, we are looking now from, it's a macro view. It's a view from above, so forget details. We just want to see what's going on. So there is a question, if you take a finite game, does it have a correlated equilibrium? Okay? So the answer that everybody gives, of course, because Nash already proved in his thesis in 1950 that every finite game has a Nash equilibrium, and all Nash equilibria are correlated equilibria. So there exists correlated equilibria. Okay? Now, of course, the proof that Nash equilibria exist uses fixed point theorem, Brouwer, Kakutani, whatever, but that requires a relatively heavy mathematical tool. On the other hand, correlated equilibrium is given by a bunch of linear inequalities. Okay? So proving existence of a solution of a linear programming problem using fixed points sounds like an overkill. Okay? And in fact, I remember Aumann used to, for many years, used to say, you know, there should be a simple proof, okay? But there wasn't a simple proof, okay? That was not, there was no simple argument giving existence of correlated equilibria. And then finally, such a proof was found. I mean, I was involved in it with David Schmeidler, I think in the late 80s. And that proof was, there is a reason for the story, you'll see. It's not just to tell you what I did, yes? There is a that's not the point, but of course, I'm telling you things that I've been involved with. So that proof was a proof that used duality, okay? I mean, linear programs used duality, but was not a simple proof. I mean, there was some trick there. I'll come to it in a moment. And also we decided, well, it's a game theory problem, and use duality from linear programming. Why not use the minimax theorem, which is equivalent to it, and it's much nicer for a game theoretic community. Let's use the minimax theorem. It's again, it wouldn't matter if you do it that way or that way, and that's what we did. Okay, so essentially, what we did, we defined an auxiliary two-person zero-sum game, and we proved some property about that game. Okay, and that property was that the value of that game, the min-max value is 0, and that was exactly equivalent to existence of correlated equilibrium. Okay? But then, and that was put aside. Then came a new thought, and then now comes another collaborator of mine, Andreu Mascolel, sorry, should be here, okay. So Andreu and I started thinking, wait a minute. Now that we have a two-person zero-sum game, from which you get correlated equilibria, two-person zero-sum games are nice creatures. For example, in terms of dynamics, there are nice dynamics that converge to optimal strategies. For two-person zero-sum game, the famous fictitious play, which is a very, very simple dynamic, converges to optimal strategies, which means we have a nice dynamic that converges to correlated equilibria, because it turns out that the correlated equilibria are exactly the optimal strategies in this auxiliary game. Okay? So we have a nice dynamic, a simple dynamic. So out of this thing came a simple dynamic converging to correlated equilibria. Well, not so simple. The reason was not so simple, and that took another 5 years or so to simplify it to the point where we wanted to get it, was that this worked in the space of n tuples of actions, which means all n players had to act together in some sense. And that's not a kosher dynamic in game theory. A kosher dynamic or an acceptable dynamic has to have every player doing his own. You cannot force everybody here, you know. I mean, maybe Jennifer, and not even them, I don't think you can force them to do anything. No, sorry, wrong example, okay. Okay, so, you know, you don't have coordinated dynamics, yes? You want to have dynamics that are decoupled. I think we used the word decoupled then, but later it became uncoupled dynamics across the players, okay? And that took some time and to do it. And they finally, the end of the story after that took some years, yes, and that's work with Andreu. Yes, I knew he's there, but came a little late, yes. So that's Andreu, which eventually led to a very nice class of dynamics, of simple dynamics, which we call regret matching, and general regret-based dynamics, which is a special, which are all uncoupled, and this notion of uncoupledness, it all came out from this, okay? So as I said, we started from who needs another proof? So we really gave another proof to a theorem that was already proved. Who cares for another mathematical proof, okay? But that proof, in the end, led to really very, very interesting stuff, okay? So that's one thing okay? So that's one story I want to tell you. Now, a second story. Christos may remember that I asked him a question at Dagstuhl some years ago, okay? You promised me an email. I still wait for that email. But you'll see that, that I'm no longer waiting for it, okay? Here is the question. How difficult is it to compute correlated equilibria? Very simple question, okay? Now, we already know it's linear programming problem, so what can one say about this? It's a trivial question, right? Well, okay, let's make it a little more precise and see how trivial it is, okay? So we have n players. And for simplicity, assume that every player has just two pure strategies, just, again, to make it simple. So that means that the number of strategy combinations is 2 to the power n, is exponential in n. Okay? So in particular, the data of the problem, which is the payoff for every player for each one of those 2 to the power n combinations, is n times 2 to the power n times whatever number of bits you need to represent it. So it's exponential in n. Okay? So the data of the problem is exponential in n. Okay? Now, to compute a correlated equilibrium, we have 2 to the power n unknowns. Those are the probabilities you assign to each cell, to each action combination. Okay? And the number of constraints for every player, there are 2 constraints. When he's supposed to play action 1, he doesn't switch to 2. Doesn't matter. If you don't know correlated, believe me, 2 constraints. Okay? I won't go into it. Those who know anyway, I'm not going to add anything, and those who don't, I'm not going to add anything either. So with this one sentence. So every player has 2 constraints, then some probability is 1, so it's 2n plus 1. Okay, anyway, so it's linear in n number of constraints, exponential in n number of unknowns. A linear programming problem of this size can be solved in time that is exponential in n. Okay? I mean polynomial in 2 to the power n, which means exponential in n. Okay? Now, can be solved. Can it be done in any better way? Okay? So that's a question I asked Christos. I don't know if you remember, but it was after a lot of glasses of wine, I think. It was some evening there. Okay? At Dagstuhl, no, they have good wine there. They have good wine there. No. You didn't come, you see. That's what you missed. Okay. So is the computation of correlated equilibria an easier problem? Okay. So, okay. So now here is some interesting fact. Okay? There exist randomized algorithms. For example, those regret matching that I told you in the previous slide, that can find an approximate correlated equilibrium. Approximate correlated equilibrium means that you satisfy all the constraints within epsilon. Okay? Like an approximate solution of the LP program. Find this with high probability in a number of steps that is polynomial in n. Okay? Now, that at first sight should be a big surprise. The data of the problem is exponential in n, and you find a solution in time that is polynomial in n. In fact, you're only checking polynomially many cells, many entries in your matrix. That sounds wrong, but then you realize that for LP problems, there is always a basic solution that has no more than the number of constraints, non-zero elements. So then you realize that that's not such a big surprise. But it's still a surprise, because if you look at linear programming problems of this size, they don't have this property. Okay? We do not have randomized approximate algorithms for linear programming problems that are of exponential in n size that can find an approximate solution in polynomial time. There are no such things. Okay? I'm not sure if there is a theorem saying there cannot be such things, but I'm sure there aren't anyone knows. No. I think it's a good question. So the question is, okay, so correlated equilibria have something special going about them. Now, how about finding exact correlated equilibria? How about finding, it's not the battery. It's just, no, never mind. I can keep pressing, but okay. How about deterministic algorithms rather than randomized algorithms? Okay, so that's a question that I kept asking. In fact, Nicole probably remembers at the half a year that we had in Jerusalem and in other instances I kept asking, and everyone said, it's a good question. So what's the answer? Okay, I didn't get any answer. So then Noam and I decided we have to look at this problem seriously, and we did. In fact, while I visited MSR in Mountain View, okay, so that was a useful visit, just to connect it to MSR. And then, okay, so here is, okay, so we have a 2-by-2 table now, approximate correlated equilibria and exact correlated equilibria. That's what you want to get to. And then algorithm can be randomized or deterministic. And as I said, this cell is poly n. And turns out that all the other cells are exponentially in n. There is no way to get it faster than exponentially in n. Okay? So all the other cells behave like standard linear programming of this size. Again, I'm not sure about the constants, but so what we are really doing is counting queries. Queries means you are looking at a cell in the matrix and asking what the payoff is there. So it's counting. It's a query complexity if you want to be precise. If we want to be precise, so it's not you, just you. Okay. Anyway, what happens is that so the question is, why is there? Sorry. Okay. So the big question is, why is this cell different? Then why is this cell special? Okay, I think I understand why it is different. And that is exactly to the fact that the dual is uncoupled. Namely, when you look at the dual problem, you can uncouple the problem across the players. And Christos also knows this from his work on computing correlated equilibria. It's exactly that trick. However, the big question, which is still I don't understand, is why does it help only in this cell and not in the other cells? Okay, that's still a mystery. Why is this uncoupled property of the dual helpful only here and not in the other cells? Okay, it's still a mystery, so there is still something to do. Okay. Okay. Now I want to throw that. In fact, I think was why Nicole invited me here. She just heard me made some comment in Dagstuhl, and then she said, "Okay, you have to come and make this game." Okay. So complexity is something that is a very common buzzword here. Yes. So there is computational complexity. There is communication complexity, and I'm sure there are lots of other complexities, complex complexities, I don't know, whatever. But so you take a problem and you say, look, this problem, the complexity of this problem is NP or PPAD, or there are lots of classes. I stop at, so I'm sorry to say, NP is where I stop. There, beyond that, I don't really know. But anyway, one can say exactly in what class it is. One can say exactly as a function of the data how fast or how slow the computation of the solution goes, okay? But is that all? So I think that there may be something beyond that, and I want to propose something that I call conceptual complexity. So even if you have, so does the computational complexity capture all the difficulty of a problem? And what I want to suggest that maybe not. Then even after you have a precise solution, you may have a precise solution, but you may have no understanding of what the solution means, okay? What it represents, what the structure is, how does it change, what does it do, okay? And here I have a simple example. Those that were yesterday at my talk will sure understand what I'm talking about. But even that, suppose that there are two goods. There is one seller, one buyer, and two goods, and the seller wants to sell those goods and get maximum revenue, okay? And suppose that each good just has 10 possible values. Okay, there are 10 possible values with some probabilities. Okay, then the solution is going to be 300 numbers. Okay, it's the probability of in each one of those 10 by 10 combinations, probability of getting good 1, probability of getting good 2, and how much the payment is. So you're going to get 300 numbers. Beautiful. Those numbers are going to be something like, even if you start with very, very simple data, are going to be something like 7,233,000 something divided by 17 millions or something, okay? That's the probability of getting good 1. Now, somebody hired you to give them the answer, and you come with this answer, of course, you know what's going to happen, okay? I mean, go away. What is this? I mean, you want me to sell with probability 17 million divided by 23,027,000? I mean, this is ridiculous, okay? So we get precise answers. May take a long time or a short time. In fact, people have got very nice results on how to do this in a very efficient way. But we still do not understand the answer. We don't understand the structure of the answer. Yes, which is in some sense. Now one could say if it is difficult to compute, it's probably also difficult to understand. But that doesn't always go in hand. It may be easy to compute and you get a very complicated answer that you don't understand the structure. So you can just give numbers, but you don't know what it means. You don't know how to use it. Okay, it's not very useful. Okay, so maybe it's connected also with how difficult it is to represent the solution. I don't know. It's some conceptual thoughts on some complexity that may go beyond how difficult it is to compute. Okay, it's how difficult it is to understand the structure of the problem. Okay, okay. So now I only have 1 minute. Okay, sorry. So as I said, computer science and economics are very different disciplines. Okay, they work at in very different ways. And again, economics or game theory and so on, different research paths and strategies. So I'll just give you a quote from Noam Nissan's blog. Okay, Noam Nissan, has a blog. So that was written in 2010, and he quotes me correctly. That's what I told him. So we had some nice results, Andrea and me, and so when I was asked how he should refer to that, I said, look, if we had been computer scientists, we'd be in a conference by now. Since we are economists, it will take a couple of years until these are preliminary thoughts. So what happened? Noam wrote the theorem and the proof in his blog. It was already there in 2010. I will tell you now the good news. September 2013, which means a few weeks ago, it finally came out as a discussion paper. Okay, so now it exists. Well, there have been some changes and some improvements and so on, but that shows you something about the difference in the pace of the two disciplines. Okay, and that is not just how fast things are moving. It's also well, I only have. Can I have 1 more minute, or you take it out of the extra time to respond? Yes. So no, you get your 25 minutes. You get You get your 25. I will not reply to you. Yes, okay. Okay. So for example, work that I've been doing with Noam Nissan lately. So I'll tell you another story. I mean, so we did the work immediately. Oh, this goes to this conference. You already had the box which conference it goes. Yes, because you have to send it to a conference. And so, okay, there is a deadline. You have 1 week to write this. Okay, so write it. Then I say, no, we can't send this anywhere. I mean, I'm ashamed. We have to work on this. This is not. Okay, we work for 1 week. And the end of 1 week, or that week, Noam said, look, this is the most I ever spent on writing something that is submitted to a conference. And I said, this doesn't even start to look like a paper I'm willing to send anywhere. Okay? That tells you, so I said, okay, you sent it to the conference. Now I'm going to rewrite this from scratch as I think this should be written. Well, that was 1.5 years ago. I've started. Okay? So at some point it will come. But so those disciplines really move at different pace. Now there are advantages and disadvantages. Yes, I won't say that one model is better than the other. There are some advantages. In the computer science, especially given the large number of people and students and so on, so when as Noam said, if it does something, immediately there are 10 students that will work on it. Well, I don't have 10 students, yes? So things that I'm not going to do, I may have 1 student or 2, sometimes will never be done. So one should really get into it. By the way, Noam also said that extra week that he worked was not a waste of time at the end, because we got some new things out of it. Okay, so I'll just, let me just say, okay, I'll just end. I mean, I have lots of stories to tell about this, but in any case, the summary is that this has been, and I think is going to be, an extremely, extremely fruitful interface. Okay, and I think that we are talking much better, that the communities are talking much better to one another. Of course, each one has its own thing, and I think that you know this person. I think that probably he is, okay, he's a proud father, right, of the two disciplines. Okay.
Thank you very much. So we're going to hold questions for the round table at the end. We'll have 10 minutes of a chit-chat between the two of them and the rest of you. So our next speaker is Christos Papadimitriou. I think he doesn't really need any introduction in this community, but he's a computer scientist from Berkeley and has worked a lot on the complexity of computing equilibria and various other foundational things in computer science. Floor is yours.
All right. So many thanks, Nicole. I'll do what I'll keep doing what Sergius do. Press this button and nothing happens. Okay, so that's very all right. So great. Oops. Okay. All right. So worse than nothing. Okay. It's the length of my name. You know, it distorts everything it goes into. Yeah, that's yeah. All machines lose the sense of scale. So let me start. I mean, so what I want to start with is I want to tell you my path to this business, how I started on algorithmic game theory, as we call our discipline, and that's a very interesting story. It started exactly 30 years ago, almost to the day, during a lunch with a famous man, Kenneth Arrow. We were colleagues at Stanford, at the Operations Research Department, and he invited me to lunch, and it was a fascinating lunch. I had a great time trying to keep up with what he was telling me, and at some point he took out of his briefcase a paper and gave it to me and told me, "I think you should read this." And I had it just here. I almost told him, you know, I'm not your graduate student buddy, okay? But then I said, he looks like a clever man, so I better listen to what he tells me. So, it was not a good paper, so I'm not going to tell you which paper it was, okay? You know, but it was an ingeniously selected paper. It's the kind of bad paper that makes you, draws you in, okay? Makes you want to work on this area, okay? So, and that's sort of my path. You know, after that, I started talking with Nimrod Megiddo, a computer scientist and game theorist, who was sort of in the direction of this field. We started thinking about equilibria. Then I had a student who was interested in game theory, Deng Xiaotie. He wrote his thesis at Stanford on computational aspects, complex aspects of collaborative game theory. Then, as Sergio was kind to mention, I worked on bounded rationality. And this story gets to a point where it's like this famous interview by a billionaire. The journalist asked him, "How did you get here?" And he said, "Well, I started as a poor orphan in Brooklyn, and I had 5 cents. I bought an apple. I cleaned it, I polished it, I sold it for 20 cents. I got 5 apples for 4 cents each with the result. I polished them, I cleaned them. I had sold 2, and then I found out that my uncle had died and left me $3 million. Okay, yeah, so this. So I mean, and the reason is that as I was doing this work, something completely tectonic was happening, okay, you know, and of course I'm talking about the internet, okay, and this, another story, this a book I just threw away, okay, I mean, I found it in my library, right, I mean, and it was very humbling to realize that in 1994, I thought that it's worth buying a book. I guess it's probably more humbling for O'Reilly, okay, you know, where it's worth buying a book whose title is the whole internet, okay, you know, so it's yeah. In any event, the internet, and immediately sort of, you know, I realized that the game had changed, okay? My life had changed, okay? That the computer was no longer worth studying, okay? The computer was the gadget that brought us this monster, okay? So now we have to study this, all right? I mean, and to study the internet, you really have to understand people, incentives, and so on. I mean, also, to put it in the eloquent words of my colleague Scott Schenker, the internet is an equilibrium, okay? We just have to identify the game, all right? So, speaking of equilibria, that's a good place to start. That's where we started, because what's equilibrium? I mean, so here's an equilibrium. The mango would love to be at the bottom of the bowl, okay? But since nobody's moving, it will stay there, okay? So this is exactly what equilibrium is. So, And the story of equilibria is rich and old. It started with von Neumann, our father. And they always exist in two zero-sum games. And of course, famously, Nash proved in his thesis that even in non-zero-sum multiplayer games, and I mean, inspired by this wonderful result, which in some sense changed not only game theory, but all of mathematical economics, Arrow and Debré proved that in markets also, right? I mean, and as a newcomer computer scientist, okay, there is an obvious question to ask, okay, but can they be computed efficiently, okay? And this is, of course, understandable reflex for somebody like me, with my, and of course, everybody in the right mind, all economists, certainly at the beginning, some of them still now, they ask, but why should we care about algorithms for equilibria, right? And I think that there is a reason, okay, that economics should care about algorithms for equilibria. And here is why. Because equilibria are predictions of behavior. And when you propose a way to predict behavior, computational tractability is important, okay? Is essential, is necessary. To put it in the eloquent words of Kamal Jain, if your laptop can find it, neither can the market. Okay? So, for example, if you tell me that your market is going to solve satisfiability, I really want to see your market. Okay? Okay. So, here's what I'm saying, right? I mean, that in some sense, game theory, in many ways, was a beauty contest among solution concepts. Okay, all I'm saying is that computational complexity should be one of the judges. Okay, so all right, cool. So a few years back, with Kostas and Paul Goldberg, we proved that finding equilibrium is indeed intractable, a Nash equilibrium. All right. Now, it's true that Roger Myerson, 15 years ago, wrote that the Nash equilibrium and its universality, in other words, Nash's theorem that every game has one, lie at the foundations of modern economic thought. Okay, so this is something about the marriage of computer science and economics. Okay, mathematical economics. Okay, that it starts with trouble. Okay, because there seems to be a computational hole in the foundation of modern economic thought. Okay, so we have to fix this. Okay. But even before equilibria, so this is with Koutsoupias, we came up with this concept, which now it's called the price of anarchy, and this is the ratio between social optimum, the social optimum cost, and the cost of the worst equilibrium. All right. In other words, you have a bunch of people doing something. If they were a well-organized, disciplined society, they will do something which optimizes the social cost. They won't, okay? They will try to optimize each their own, and they're going to end up with a Nash equilibrium. How bad can this be, all right? That's the question. And here is a classical example. Many of you have shown it. It came up in traffic, in transportation research a few years back. And basically it says that, imagine that you have this network. It's a road network, all right? I mean, these are the delays. This is 1 hour. This is a strange road, okay? If basically 1,000 cars want to go from here to there, and the delay here is going to be proportional to the if half the cars take it, it's going to be half an hour. If 3/4 of the cars take it, it's going to be 45 minutes, all right? I mean, so it's and you make up the story about this zero link, okay? So the point is that if you want to optimize to find the social optimum, you should instruct half the drivers to go this way and half the drivers to go this way, and this way they're going to arrive in 1 hour and a half. If you let them to their own devices, believe me, they're going to do this, and they're going to arrive after 2 hours, okay? So it turns out that the price of anarchy in this situation, this is the worst possible example, all right? And the price of anarchy in this situation, it is 4/3, all right? Which is 2 divided by 1.5, all right? I mean, and this is a wonderful result by Ravgad and Retardos that popularized this concept. And the question is, why did computer science have to come up with this concept, all right? I mean, and there is an explanation, and here's my explanation, that economists had always had to live with anarchy, okay? So and they are not aware of it and of its price, all right? I mean, and only CS will remember with nostalgia to the good old days where we could design things, okay? You know, so, and of course we love ratios, okay? Okay, mechanism design, okay? So this is a very important field, and it's another wonderful, you know, also Sergio talked eloquently about it. It's a wonderful arena for interface between computer science and economics. And design the game, you want to design the game so that selfish players do what you want, okay? And in some sense, this story is a wonderful example of mechanism design, because Leon Hurwitz, half a century ago, came up with a model so deep, so elegant, so open-ended, so full of wonderful problems, so relevant, that it was basically an incentive for all clever mathematical economists to start competing. Who is going to prove the more important theorems in it? So in the end, the winners emerged. Okay, you know, so that in this game. Okay, so and of course, these three people got the Eric Maskin and Roger Myerson shared the Nobel Prize a few years back. And of course, the great example of mechanism design is auctions. And we all know that second prize Vickrey auction is truthful. In other words, you always are incentivized to represent your interests accurately and optimize the social welfare. And also it generalizes, and it was observed a few years later, a decade or so later. And then, amazing result, Myerson showed that if you want to sell a single item and you have independent priors of how much this is worth to your bidders, you can maximize revenue by a simple protocol, okay, which basically reduces the problem to VCG. But there are some gaps. There were some gaps in this theory, and what I want to point out is that in some sense there were gaps that require the kind of collaboration between economists and computer scientists for them to be filled. And then in 1998, Noam, Nissan, and Ronen came up with algorithmic mechanism design. Okay, so you know that was, I believe that was the title of their paper. They basically rubbed this problem to our faces. Okay, you know that there are computational, wonderful algorithmic complexity computational questions in mechanism design. Okay, and that we should work on them, and had some wonderful first results there. And we didn't need Nissan and Ronen, you know, because they were in the air. Okay, you know, auctions were in the air because eBay was online and AdWords auctions had started. All right, I mean, so this was about the same time, and a lot of many computer scientists went to work, but of course I will show my work. Okay, you know that the correlated bidders was solved. You know, we figured it out with George Pierakos. Sergio and Noam have done amazing work, and others had amazing work on two-item auctions. And as an extra bonus, a new theory algorithmic theory of mechanism design has emerged from all this due to Kostas and his group at MIT. All right. If you are nearly as old as I am, the first program you wrote was not Hello World. It was this program, all right? I mean, it was how do you compute the max of an array, all right? I mean, so your old friend Max, okay, you shouldn't forget him, okay? So why am I saying this? Okay, the world has changed, all right? You know, remember that, you know, Alan Turing told us what computation is, right? I mean, but since then there have been a lot of friendly amendments. Okay, people said no, computation is parallel. No, it's actually reactive. There is not input-output. It's not deterministic, distributed, quantum, and so on. Right. So what I'm saying is that this interface and the internet has brought us in front of a really different kind of computation, a new form of computation, incentive-compatible computation, if you wish. Your inputs, even your gates, okay, but let's not talk about this, are selfish agents. And these selfish agents are keenly interested in the outcome of your computation, okay? Life is not simple. Okay, you get it? So, your inputs are selfish agents who want you to, who have a say of what they want you to compute. So there is no other way but to give them incentives to tell you or not to lie too much, okay? Incentives are now an integral part of computation, all right? Vickrey auction is the new max, okay? If you want to find the maximum of n numbers, what do? You bribe the bastards, okay? You give them incentives to tell you the truth, all right? Okay. And here is a question, okay? Now I'm appealing to my fellow theoreticians. What happens to our familiar categories like AP, NP complete, and so on, okay? It turns out that because of VCG, of the generalized of Vickrey auction, the incentive-compatible variant of P is the same as P, okay? Nothing changes. For the same reason, the complication of incentives is not going to make any problem easy, okay? So NP complete stays NP complete. Okay, here is a surprise. Something does change. APX, which is the class of all optimization problems for which we can deliver a constant factor approximation, shrinks, okay? There is a problem which, if you don't need to have incentive-compatible computation, you can approximate fine. But if you have an incentive-compatible computation, you can't. And that's work with Singer and Shapira back in 5 years ago. And there is an array of important problems here, which I summarize here. What happens outside this very specific domain environment, which is where Vickrey auction is possible? Okay. All right. So I have a few minutes. So I want to tell you something else. Okay, that the other great dividend from working in a new area, for working in the interface between two disciplines, is that you enrich your obsessions, okay? The things that you are absolutely obsessed and you sort of see around you no matter where you look, okay? So, for example, now games are one of my obsessions, right? Because before they were not, okay? So, this gives you, it basically enriches you as a scientist. So let me tell you this story, okay? In the past 6-7 years, I've been also very interested in evolution, okay, in understanding evolution, how we came to be. In other words, here is my favorite computational way of pinpointing the mystery of evolution. Okay, look around you. Okay, what algorithm could have produced all this in a mere trillion steps? Trillion, okay? Trillion sounds like a big number, okay? But if you think about it, your cell phone has done 1 trillion steps since the beginning of my talk, okay? And it hasn't accomplished much, all right? So believe it or not, we have the answer. We know which algorithm has produced all this in 1 trillion steps. Okay, should I skip it? Okay, I'll show it to you. All right, so here's the theorem. So let me proceed to, So there is a very standard mathematical model initiated by Fisher, Wright, and Haldane in the 1920s. All right, whereby geneticists encode how we came about. Okay, how populations evolve. All right, and basically it is a mathematical framework. It's called population genetics. It's if you wish, at some point, it's a differential equation, all right? It's a differential equation that tells you how populations, basically how natural selection leads populations to change, all right? Essentially to change their genetic makeup. If you wish, to change the alleles in the population mix, all right? I mean, so that's what it is. And the point is that if you look at this equation long enough, and you make the right simplifications, and you are in the same frame of mind, the right frame of mind, you end up with a really interesting connection. So here is the theorem. The theorem is that joint work with Livnat, Chastain, and Umesh Vazirani, evolution of a population, in other words, how the genetic mix of population evolves over time, can be seen is mathematically identical to a coordination game. Coordination games are the simplest, most boring kind of game where there is no conflict, but everybody has the same utility, all right? And so coordination games are interesting only in cases where the players are cognitively challenged, okay, like genes, all right? I mean, so because the players here are genes, okay? And the strategies of the genes are the alleles, okay? Every gene has a few alleles. And the probabilities, so there is a game, right? And people randomize to play games. The genes randomize, and the randomization is the frequency of the alleles in the population, okay? And the common utility, I told you, I warned you, that's a coordination game. It's a boring kind of game, okay? There is no conflict. The common utility that everybody is aspiring to, by this sort of groping way, increase is the organism's fitness, okay? So this is not the selfish gene. I mean, it's a game, but it's not Joe Dawkins' selfish gene. It's the community-minded gene, okay? I mean, it's the gene that sort of that only cares about the organism's fitness. Are you ready for this? The game is played through multiplicative weights update algorithm, okay? What sometimes is called boosting, okay? So it's done by machine learning, okay? You know, can you believe this? I mean, so this is the algorithm that brought us all here, okay? So that's in any event. The algorithmic game theory, I believe it's thriving, okay? It has there is a lot of excitement. There are a lot of great results all the time, okay? So because we're a new field, we are of course insecure. So once in a while we get together and we say, are we done? Is this the end? Will there be something? And then boom, sort of a new result. And so we have both senior researchers and young people. We have both economists and theoretical computer science work on this. We have both depth and style, I think. We have conferences. We have a journal and a half. Thank you, Ehud. And actually, it also has an institutional champion. Okay, so happy birthday, right?
Thank you very much for that great pair of talks. I'd like to invite Sergio back up and both of you to come to the front of the room. We have here, table and chairs for you. And I just wanted to give you an opportunity to discuss with each other and comment. Sure, that's fine. Comment on each other's talks and.
Well, I must say that I very strongly agree with everything you said. I mean, yes, sorry. I mean, you didn't say anything that I can argue about.
Okay, that's always surprising. That's always surprising me. So, I mean, actually, I think that Noam's admiration for me went up by 10 times when I came to give a talk at the Center for Rationality, and I finished my talk without being interrupted away at the third slide. Okay, so
okay. My bad.
So this is embarrassing. I mean, if we don't have things to fight about, I mean, maybe we can have, or we can have questions from the audience, right?
I think that will be the best.
We can take audience questions. Yes.
So the last thing you said about evolution proceeding by boosting, Can you just help us with that a little bit? I mean, what are the weights in the evolutionary process?
Oh, it's precisely the expected fitness of each allele in the current population mix.
And I mean, those weights are sort of stored somewhere?
No. Only the frequencies. The system memory are only the frequencies. So the population keeps its state. Yeah. The state is only the frequencies. Okay, and of course there is the hidden state, which is the fitness, sort of, you know, the natural selection value of each genome, or genotype. You know, if you are interested, there is an archive paper on this with Vazirani Papadimitri, who have written a paper for 30 years. Okay, so,
David, yes.
Yeah, it still seems like there's the question of, is a trillion steps of hill climbing and boosting, is that really enough to get us to human beings?
No. So listen, okay, sort of, you know, nothing can really explain. So I think that this is a productive new way of understanding what happened. Okay, you know, so since we are focusing on that, a couple of wordings. This is, I mean, no, in some sense, this is what I'm bragging about. This is about evolution between mutations. Okay, all right. So there are mutations, and everybody's focusing into modeling mutations. But I mean, what happens between mutations? And this actually happens between mutations. Mutations are important. Okay, they provide the diversity. Another thing about boosting is the following, right? I mean, that if you analyze, you can analyze mathematical boosting and call it and see that essentially it is gradient descent for solving a convex programming problem. Okay, and the convex programming problem it solves is basically the objective is a combination between regret and the entropy of the distribution, and in some sense, it is this algorithm that keeps variance around, keeps genetic variation around. Okay, so you know, because in some sense, in most classical models of evolution, you go to a hill. This means that variance is lost, variation is lost. Okay, so you know that you have one allele from each gene, and then you have to start from the beginning.
Madhu?
So I just wanted to find out, I mean, it's been said that the importance of Nash equilibrium as a solution concept has come down a bit, given that we understand that it may be intractable in some cases. So what are your reactions to this?
It's trying to say
So the question was about the the fact that Nash equilibria is hard to compute in some sense has deflated the enthusiasm for it, and what sort of alternate, or how do you feel about this, I guess?
Well, yeah, I'm on. So there was a point on my last slide, or one before last slide, I mean, that I didn't talk about, and that's one of the I would say in game theory, game theory is a discipline, okay? And the discipline, at least for not for everyone, but for many people, and I subscribe to this school, it's a discipline in saying, look, you are not inventing a new solution concept for each problem, okay? One can always take a problem, you know, and say, okay, we have duopoly, we have this solution, we have monopoly, there is another solution, we have auctions, there is another solution, and so on. What you want a solution concept, you want a universal solution concept that is a good one, and then you apply it all across, and then you see what you get, okay? Now, Nash equilibrium is definitely such a solution concept. By the way, there have been in game theory various refinements, okay? You may know subgame perfect equilibria, trembling hand, proper, sequential, and so on. Some of those things, I mean, there was a period where lots of people worked on it. Some of those things survived, those that are really very basic. Others, you never hear about them anymore, okay? Because they're very much tailored to specific problems, okay? So Nash equilibrium is there to stay. Now, the fact that it is difficult to reach, that's also there to stay. That says something about the problem, Okay, it doesn't say something about the solution concept. It says something. In some cases, it is indeed very difficult to reach equilibrium, which means the dynamical system may well wander around very long time and wander around and reach equilibrium, you know, like we heard the talks this morning, at an age that is more than the that it takes to factor the two numbers, right? The to factor into primes, yes? May take longer, which means that perhaps the Nash equilibrium is the wrong concept because it's not going to happen, okay? But it's there to be. Now, there are, of course, correlated equilibria, there are other notions, so it is important to know the computational properties of that, but that doesn't say it becomes less interesting.
Yeah, I agree. You know, yeah, that's embarrassing.
I mean, she was expecting a knife
yeah.
fight, and I'm sorry, you can't provide that. You know.
So we, I mean, when we proved that, you know, when we were trying to prove this, I mean, we thought that it makes Nash equilibrium less of an immaculate, you know, more interesting, less immaculate concept. So you know, so. Actually, you know, I gave a talk at the Institute for Advanced Studies a couple of years ago about that, and John Nash was in the talk, and then we had lunch later, and that's exactly his position. Okay, so you know that the Nash equilibrium will stay, and so you know what you proved makes this more interesting. You know, so. Yeah.
I think we have time maybe for one more question.
And I come from a mathematical background, so I kind of favor the economic strategy, which is write your result up carefully, find the right place to put it, and then publish it, versus writing to the conference deadlines. Would you care to comment on this?
Yeah. So I mean, there is so you know. I hate to say this, but I totally agree with Sergio. So you know that we are jumping to the conference deadline sort of way too much. Okay, so you know that. Now, your question was sociological. So the question is why, right? I mean, what makes us do that? Okay, so I mean, we are not teenagers anymore, okay, you know, but the field is young, so you know, so it has sort of, you know, some energy. It also has a paradigm, sort of, you know, that speed is vitally important, okay, so you know that Moore's law, okay, you know, so it attracts people, but you know what? When I first, I should finish with that. I don't want to go any further. Okay, you know. But when I first started rubbing shoulders to game theories, what amazed me, okay, this is the similarity of the two communities, TCS and game theories. Okay, so you know, even down to the lunch jokes, sort of, you know. Sort of density in Israelis, sort of, you know, so you know, it's you know, all these, you know, it's you know, I felt like sort of, you know, I had stepped into soda or stock or something. You know, when I started going to meetings of game theories. Yeah, so you know, it's very surprising then. What tradition, you know, what power tradition has, okay? So, you know, that one tradition, the young people in game theory, obviously they are every bit as aggressive and ambitious as we are, as our young people are. And yet, sort of, you know, they abide by the old generations habits of sitting on the paper. Sorry, you know, I'm not, you know, but yeah, I've been waiting for his papers to come out, you know, for far too long. I mean, you know, but
He's
you know,
waiting for your email too.
Yeah, I know, yeah. So to his credit, he, you know, I always, you know, when he becomes available, he does send me an email. Okay, so,
Do you think it affects the rate of progress?
Yeah.
Do you think it affects the rate of progress in these two different strategies?
I think so. Yeah. So I mean, there are several results, several major results in theory that would be impossible with this tradition. For example, the Samir's theorem. You know, just to name one. Yeah.
you
On the other hand, yes. On the other hand, so we have to disagree a little. Yes. Yes. So it reminded me that there was a quote about last night about economists. So there was we talked about this of Truman, I think, one president looking for a one-handed economist because he had enough of those economists saying on the one hand that, on the other hand that. He wanted that. So on the other hand, yes. So sometimes, so I think there is another facet, another aspect of that, which is that sometimes it looks like, okay, there is only one final epsilon that one looks at. I mean, you can only epsilon. Sometimes the most important thing is that last epsilon, okay? Sometimes the real understanding and lots of new things come out from that last epsilon. Now, I must confess and that I've seen enough times in computer science leaving that last epsilon as it is and not getting into it and missing really on important things, okay? So, and that's part of it that, you wrote a paper and they went to the conference, that's it, what's the next subject? Yes, and people don't have the patience to really get deep and really try to understand really what's going on, okay? And there is a difference. Now, I must say that probably I'm an example of a very extremely, I mean, I'm at the extreme of being extremely slow in this aspect, and I don't think that's a right strategy either. But I think that one should, again, at least after you have tenure, yes? One should take the time to take the problem and really try to understand it, not just get a few more theorems, okay? And that's very important. And I think that the conference, papers at conferences is not good for that.
Okay.
I agree.
Thank you very much. I see Christian giving me evil eyes.
Okay.